Okay. Let's do this. The polynomial blah 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 blah, where p is a constant, has 4 integer zeros. Find the sum of all possible values of p. So, we could just factor this like a quadratic, because it's just a quadratic squared. So, I think it's a quadratic squared. No, if it's a quadratic squared, then it doesn't have 4 integer zeros. If it has 4 integer zeros, it means you can multiply to p the factors of p a plus b plus c plus d equals negative 65, right? Well, let's just say you have a quadratic, and you have x squared minus 12x, right, plus something. So you have to have two things that multiply to negative 12, and two things that add to negative 12, two things that multiply to that. And then 8 times b times c times d equals negative 65. Negative 65 can be, and these all have to be integers, so negative 65 can be split up into, let's just get rid of the negative for now. 65 can be split up into 13 and 5, right? Yeah. So then, wait, they don't need to multiply to negative 65, what am I talking about? They multiply to p. A, B, C, D equals p. So, if this is our only condition, then why don't we have like a ton of p's? We have like so many p's, right? Do we have infinite p's? Oh, no. What am I talking about? If we can factor this to a x plus a, x plus b, x plus c, x plus d, then we know that x, oh my gosh, wait, am I gonna have to, okay, x squared plus 2abx plus ab, and then just the same thing, x squared plus 2abx plus cd, and then just multiply this again, x to the 4 plus 2abx squared x cubed plus, no, I shouldn't do ab, I'm multiplying x squared by everything, so x squared, this would be cd x squared plus x to 3 plus cdx squared. Then we'll move on to this, plus 2abx cubed plus, oh, oh shoot, for a b c d x squared right? This is CD, doesn't look like CD. And then, this is 2CDX, right? Because it's x times d plus x times c. No, I did it wrong. Gosh darn it. Gosh darn it. Okay. Now let's get back to, I think it was, oh no, it was slightly smaller. Yeah, that's about good. X squared plus a plus b, x plus ab times x squared plus c, no, plus ax plus dx plus ab. X squared plus dx plus, yeah. Right? And then let's just find all of the cube terms. So we know we have here x cubed times c plus d. So we had that. We have this plus a plus b x cubed. I think that's it, right? That one times that one and that one times that one. Yeah. So a plus b plus c plus d must be equal to 0. That makes no sense. What? Okay, let's just go with that for now. I mean, I think I did this wrong anyways. And then let's find all of the linear terms. So we have x squared, there's nothing. So there's cd times a plus b x. Then there's plus ab times c plus d x. So it's ACD, well, ACD plus BCD plus ABC plus ABD all times x. So this equals 0. Okay. Is this all just all the combinations of the things minus 1? What? I'm trying to think how this can be done. Well, if we're adding all these together, then at least we can know that A, B, C, and D cannot, oh, and P is equal to A, B, C, D. P is equal to A, B, C, D. They cannot all be positive. Some have to be negative, of course, because you can't add everything, you know. So let's call A negative for now. If A is negative and everything else is positive, then we have positive plus negative plus negative plus negative. Which likely is not it. Because I'm just thinking, you would have two, so A and C are both negative. So AC, then that'd make this positive, that'd make this negative, that'd make this positive, that'd make this negative. No, that's probably it. I don't know. I'm just gonna check the answer, because I really have no idea. To have four integer zeros, the polynomial must factor into a plus a times x minus a, and x plus b times x minus b. Okay, I guess that's because it's of this form, and then they just simplified that. Therefore, we need pairs of perfect squares that add to 65. There are two, they listed the two, and they gave the possible values. Okay. Thank you guys for watching. I didn't get that one, but hopefully I'll get the next one. See you guys whenever you see you guys. Bye.